Hi folks, look, a whiteboard, home from home. Big shout out to the Hastings crew. This is going to be, by request, this is one of the exam questions or moments that I posted, and Oliver has asked me to have a look at this. So let's have a see what we get. So I've drawn my diagram. Hopefully you can see that. It's right near the top of my board. And we've got a gymnast hanging off the beam. And of course, draw your diagram huge if you can. It's got two ropes that are suspending this beam, and we've got quite a lot of the distances. These were on the diagram, and we've got the distance to the centre, and we've got the distances from the end here. So the question's actually asking us to show what, in terms of x, what we get when we work out T, the tension in the beam at P. So TP, if I can call it, is what we're looking for. So what's missing from this diagram, what they haven't put on any of our forces. So let's have a look at what forces we've got. Well, we've definitely this beam, and that is going to tensions in the ropes. So they weren't necessarily the same. So I'm going to call them TP and TQ. We've also got the weight of the beam itself, which in the question it does say it's a uniform rod. So that means that it's going to be in the centre. That's the weight of the beam. And it gives us that. That is 20 kilos. The mass is 20 kilos. So we've got 20 as our force there. We've also got the only last force we've got here is this gymnast that's hanging off, and the weight of the gymnast is so the weight they're exerting, the force they're exerting is 50 g there, and they are the distance of x from P. So that's an unknown that's going to sort of hang around. Now we can always resolve forcing horizontally. There's nothing being that way, there's nothing pushing it that way. So that's all in equilibrium. And this whole system is in equilibrium. But we do have this equilibrium in a vertical direction. So I'm going to park this over here because we might use it later. Is that the force is upwards, TP. If I add that to TQ, then I'm going to get a balance with these two forces acting downwards, the 20 plus the 50 plus the 20. So that gives me a nice result, TP plus TQ. So if I know one of them, I can work out the other one. I'm not going to get rid of my G yet, although we will use 9.8 as G. Okay, so that doesn't directly tell me what TP is, that's what I'm trying to find. I've got this other unknown, TQ, and when we're taking moments, which place to take moments about? It's in equilibrium. We could moments here, here, Q, or all at B, equilibrium. However, if we want to work P is, so if we took moments about A, we would get an equation involving TP, TQ, and these two weights here. If we took moments about P, this force here would no longer have any moment because it's acting P. Its perpendicular distance is 0. So we would be able to find TQ versus these two. They would balance out. But actually we want to find TP, and what we don't care about yet is TQ. So I'm going to take that TQ, about Q rather, so that I no longer have a TQ in my equation. So it's all about choosing the point. Take your time at the start of these questions to draw a real off, and you can get all on it. And the second tip is use a really sneaky choice of how you take your moments about. So I'm going to take my moments about Q, draw a little arrow to show that's what you're doing. This is again a maths shorthand. Just going to move over here. So we've got our moments about Q. If we look at what's twisting this one, of course TQ isn't having any effect now, but TP is, and these two are. So let's take them one. If we look at what's turning it that way or that way, well, I'm going to go with this clockwise direction first. So TP is trying to turn this clockwise. So we've got TP, the moment will be TP times its perpendicular distance. And if we've chopped off 0.3 off of each end of this 2 metre rod, then it must be 1.4 metres between the two cables. Okay. Force trying to turn it that way around Q. This way, we're trying to bend it down into the other way. We're going to get these two. This 20G is just the weight of the beam. So that will be the size of the force. Perpendicular distance 0.7. And it's also got this 50 G newtons that is also adding to that. I'm going to turn it that way. The tricky bit here is the distance away, because we don't know the distance here, but we do know it's X in between the gymnast and that pivot, that whole, so it's 1.4 minus X would be that. If this is a little bit confusing, redraw your line and cut into pieces. There'll always be, you're just taking, and this should give you your final answer eventually. So TP is the only unknown in here. This all kind of works its way out. 20 times that is 14G, plus we've got 50 times 1.4. You'd probably be faster than me on the calculator. I think that's 70, 50G X at the end. 84X. Now if you divide all that by 1.4, I'll grab my calculator. So 84 times 9.8 is 123.2. If I divide that by 1.4, 588. And the second bit, I've got 50 times 9.8, 490 by 1.4, and I get 350 on the nose. So no rounding required if you just put this calculator. So that's actually what they're looking for. We measure that in Newton. So this bit is not particularly difficult with a calculator. This is what you want to. Hopefully you can look at your own working and see how it compares, see what you got and what you didn't get. Part 2 coming soon.